In this video, we're going to learn the process for drawing Lewis structures that represent covalent compounds, and just like the process with ionic compounds, we're going to be using real compounds in order to illustrate what to do for each specific step. Step 1 is actually identical to ionic compounds in that it's always a good idea to draw the individual atoms and while doing so, count the number of valence electrons that each individual atom has. In future grades, you'll actually learn how to draw the structures of polyatomic ions, and during this process, considering the charge of a polyatomic ion is important, but for now, the priority is on the structures of the individual atoms and the number of valence electrons they bring to the compound. For this purpose, we're actually going to be drawing three compounds at the same time: H2O, also known as water, CO2, also known as carbon dioxide, and HCN, hydrogen cyanide, which is actually a very deadly poison. We can see here that we only need to look up four different elements for these two compounds on the periodic table: hydrogen, oxygen, carbon, and nitrogen. So carbon is a famous example of a compound that has 4 valence electrons because it's in group 4. Nitrogen has 5, oxygen has 6, and hydrogen in the top left only has 1. And from there, we have our starting point. So once again, we don't need to draw each individual atom. We can just note that there are 2 hydrogens in water and 2 oxygens in carbon dioxide for the purpose of our electron count. So oxygen has 6 valence electrons, and each hydrogen brings 1. And since there's 2 hydrogen, there would be 2, meaning that water has a total of 8 valence electrons that we're working with. Carbon, we see, has 4 valence electrons, and oxygen, as within water, has 6, but since there are 2 oxygens, 6 times 2 is 12 electrons that the oxygens bring, plus the 4 from carbon, meaning that carbon dioxide has 16 valence electrons in total. And finally, if we draw the structures of atoms for HCN, we can see 5 from nitrogen, 1 from hydrogen, and 4 from carbon is a total of 10 electrons. The second step is also identical to the process of drawing ionic Lewis structures, and that is to find the central atom of each of our covalent compounds. And we identify this the same way as with ionic compounds by looking for the atom that has the most unpaired valence electrons. Now, with most of these, this is quite straightforward. For example, with water, oxygen has 2 and hydrogen has 1, so we can position oxygen in the center like this. Again, it doesn't really matter where we put the hydrogens as long as they get connected to the central atom eventually. Carbon, we can see, has 4 unpaired electrons, whereas oxygen only has 2, so we can position carbon here with the 2 oxygens opposite to it. And with HCN, it's actually quite close because carbon has 4, but nitrogen only has 3, so therefore carbon is going to be our central atom with nitrogen and hydrogen off to the side like this. Now, here is where our process becomes significantly different from ionic compounds, because remember, covalent bonds form as a result of sharing of unpaired electrons. So this is where we need to connect our central atom with every peripheral atom that surrounds it with a single bond. And remember, a single bond represents a pair of electrons, 1 unpaired electron from hydrogen and 1 from oxygen in the case of this bond here. And then we do the same with carbon and the 2 oxygens in CO2, and with hydrogen and nitrogen in HCN. At this point, our electron count becomes particularly important. So for oxygen, we have added 2 electrons per bond, and there are 2 bonds, meaning we've added 4 electrons, so water would have 4 electrons left. With carbon dioxide, we've also added 2 bonds. That's a total of 4 electrons. So with carbon dioxide, there's 12 electrons that are left. And with HCN, we've added again 2 single bonds, which is a total of 4 electrons, 10 minus 4, meaning we have 6 electrons left. Up next, this is another very important reason to draw out the individual atoms, because after we connect the central atom with single bonds to each of the peripheral atoms, the next thing that we do is we put the lone pairs that exist on each of our individual atoms back on. So the way to do this is we simply look at how many lone pairs each of the starting atoms has. Hydrogen has none because it only has 1 electron, but oxygen actually has 2. So we can go ahead and put those 2 lone pairs back on oxygen like this, and with water we are actually done because the 2 lone pairs that we added come to a total of 4 electrons, meaning that oxygen now has 0 electrons left. Now the last thing to do to check our structure is to make sure that all of our elements have a full valence shell. So hydrogen can only have 2 electrons because it only has electrons in its first shell, and there are 2 electrons in each bond, so each of the hydrogens are good. With oxygen, we need to do an octet check to make sure that all 8 are present, from the lone pairs to 4, and from each of the bonds, because they're shared between oxygen and hydrogen, 6, 8, and our structure for oxygen is done. The problem is if we add in the lone pairs for HCN and for CO2, we're actually going to come up short. So let's put the 2 lone pairs back on each of the oxygens like this, and as a consequence of adding 4 lone pairs to the oxygens in CO2, 4 times 2 is 8 electrons, which means we still have 4 electrons left, and because hydrogen and carbon don't have any lone pairs, we're only going to put nitrogen's lone pair back on, meaning that we only add 2, meaning that there are also 4 electrons missing in HCN. And this is where it helps to remember what multiple bonds are. So remember, in covalent Lewis structures, a singular line only represents a single bond. But if we have 2 lines that are parallel connecting 2 different atoms, this means that we have a double bond. So after adding in lone pairs, if we still have unused electrons, we can put double bond, or indeed double bonds, into the structure. And we'll see this is particularly effective with carbon dioxide, because carbon is actually missing 4 electrons. It has 2 electrons from this bond and 2 electrons from this bond, and we still need to use 4 electrons. So if we do this, if we add 2 double bonds, we have just added our last 4 electrons in, so we have used all of the electrons that we have available. And if we do an octet check, each of the oxygens has 2, 4 from the lone pairs, 6, 8 from the bonds, so each of our oxygens is good. And because there's 2 electrons per bond, carbon has 2, 4, 6, 8, and carbon dioxide is done. The problem is, if we go to add a double bond with HCN, we add in 1 additional bond. We can't add a double bond with hydrogen because, remember, hydrogen only has 2 electrons in the first shell, meaning that it can only make 1 bond. So after we add in the double bond, we still have 2 electrons left over. But then if we remember that triple bonds actually exist, and we can show a triple bond with 3 parallel lines, this is indeed the last step of the process of drawing covalent Lewis structures. If there are still unused electrons after adding in double bonds, we can put a triple bond in like so, thereby using up the last 2 electrons that we have. And if we do an octet check, hydrogen is fine. It only needs 2 electrons. Carbon has 2, 4, 6, 8 from each of the bonds, so carbon is good. And nitrogen has 2 electrons from its lone pair, plus 4, 6, 8 from each of the 3 bonds, so HCN structure is correct as well. So following this process, we can see how to draw covalent Lewis structures, whether they have only single bonds, whether they have double bonds, or whether they have triple bonds. And this accounts for pretty much every option that exists with covalent Lewis structures. So before the next video, where we look at the naming system of covalent compounds, try yourself to draw the structure of this covalent compound here, which is a little bit tricky because it actually has multiple types of bonds, and if you need additional practice, you can try the practice problems below.